my presentation about automatic generation of digital twin models for simulation of reconfigurable robotic fabrication systems for timber prefabrication. I start with a short introduction and what this work was about, the problem that we wanted to solve in it. Will then shortly state our solution for it and conclude with, or give a conclusion and a short outlook over next possible steps that we could do in the following. So yeah, as we heard in the first presentation, the productivity of construction is still relatively low compared to manufacturing technology, and there are a lot of different reasons for that. But in recent years, I think robotics is gaining a lot more importance in prefabrication and in construction. And one reason for that is that industrial robots are very flexible and can adapt to a lot of different problems. A lot of different processes can be realized with industrial robots. They have high payloads, relatively high flexibility regarding the working area, and hence are a relatively good fit for the ever-changing different building parts that need to be fabricated in construction, and especially timber construction. And in recent years, there were a lot of very interesting developments regarding robotic prefabrication platforms in research that we have seen. And in the image, we see one, I think, very good example, a very recent example, and that was developed by ICD from the University of Stuttgart in order to prefabricate the building elements for the 2019 Buga timber shell. And we see that this platform is based on a container platform, has two high payload industrial robots and this tilt turntable, and this was used to prefabricate these timber cassettes for the Buga timber shell. And yeah, this system is very modular and is transportable, so it can be placed at local timber construction companies to do near on-site or at least local prefabrication of parts. However, it's still somehow limited in regards to the size of building elements that can be fabricated. And if we now think this idea further, we could come up with a concept of having somehow a very modular, reconfigurable fabrication system that contains of a kind of a modular system of different elements that can be placed together, that are all based on this idea of having these containers that can be transported or moved. And hence we can configure a fabrication system that can be rearranged for in between projects to adapt to new building elements that have to be fabricated. So on the left-hand side, we see that we have these different modules, which can be modules with robots or modules for handling, maybe an automated guided vehicle to do some logistics for the building parts. And on the right-hand side, there's one example of a fabrication system layout that could be realized with these modules. However, this approach offers very high flexibility and adaptability to a lot of different problems, but it's also getting relatively complex regarding control, planning, task scheduling, and yeah, there are a lot of problems that need to be solved in order to make this very efficient and at some point bring that into industry. So one thing is that for such a complex system, we need a method to describe the tasks that need to be carried out in order to fabricate certain building elements that we want to manufacture at the end. And what we're doing right now is to use a task-based description, which is stored in a task graph, which at the end holds the sequence that need to be carried out in order to build up this or to construct the building element. And on the other hand, we have the fabrication system configuration, which at the end defines which modules are arranged in what way to each other. So it holds kind of the types of the modules, the transformation in between them, defining the system layout. But the question is, how do we find a suitable combination of task schedule for the different robots and fabrication layout for a given building element or building system that needs to be fabricated. And this is quite a complex planning problem, and which can, for example, be approached using planning domain approaches like, I don't know, PDDL, the planning planning domain design language, for example. This can be used to solve these planning problems on a quite abstract level. However, in robotics, normally we have the problem that it's not possible to solve these problems entirely on this abstract levels, because at the end we need to also check at some point the inverse kinematics of the robot dynamics. Maybe also if we, for example, want to pick and place a large beam, then we definitely have to consider collisions while moving along a certain path. So at the end we need to simulate our the fabrication of the element that we want to fabricate in order to really ensure that this is feasible in reality. And then we are talking about digital twins for simulation. I think this is quite a common approach nowadays. And normally this is done by hand. So we have some this modeler, I think, that choosing its tool. It could maybe I think in architecture, probably Rhino or Grasshopper is very popular. In manufacturing, there are other tools. Would set up this digital twin simulation manually using some editor for designing it, and then loading all the data like the fabrication sequence that I mentioned into the simulation environment, carry out the simulation, and then get some result, interpret it, and then see, okay, it's working or it's not working, then maybe there are some adaptation needed. And this is somehow problematic because with this process first needs experts that know how to do that, and it's also very time consuming. Everyone who has done that at some point knows that it's quite complex, and if changes or huge changes are needed to it, that can take a lot of time. So this somehow prevents what we want to do, because in order to find this combination of building system and fabrication layout and the fabrication task description for it, probably a lot of iterations are needed, and hence we need to be able to simulate and validate these combinations very quickly. And this manual workflow that we have right now also prevents some kind of integration into an optimization loop, where we probably would need a really high amount of iterations to be carried out. So in order to solve this problem that we now have with the manual workflow in the fabrication planning that we propose a method for the automatic generation of reconfigurable digital twins. So we want to automate this whole process so that we don't need any human interaction anymore in order to set up the digital twin. We want to do that model-based, so we have some kind of description model, for example, in XML, or there are a lot of different possibilities to do that describes the fabrication units or fabrication modules that we have, the layout, the environment, maybe including the kind of the environment of the local timber construction companies, and automatically generate the simulation model. Also set up the controllers and the whole path planning system for the industrial robots that would be carried out online. So yes, and this, I think, at the end would give us the possibility to get really quick feedback about collisions, maybe singularities, if the sequence that was planned is feasible, and at the end to check if the pair of fabrication layout and fabrication tasks is feasible for production. And hence, if we are able to check that in simulation, we can make adaptations in reality really fast. So what we have is this description at the end that describes the fabrication system layout, our individual fabrication modules, like which robots do we have, where are they placed, which working areas do they have. And then we combine them into predefined fabrication modules like the TIM platform or other modules. They are based on different platforms, different robots, and different anti-factors. And then set this whole thing up using a model composer that applying model-to-model transformation techniques at the end generates all the configuration data for the simulation environment that we are using, generating the simulation model, and then feeding that into a simulation manager, which handles all the model ramp up in order to connect all the inputs and outputs, and at the end starts and starts the simulation automatically, carries it out, and then ramps the model down and generates the next iteration at the end. And this model at the end contains a list of these fabrication units that I mentioned, which are connected to our fabrication control system. It holds the environment description, which could be the local fabrication environment of the timber company, and some objects that may be there that we have to interact with. And at the end, what we get from the simulation is a result telling us whether the combination of tasks and layout is feasible, and also have the feedback on this task level stating that there may have been a collision at a certain task where the robot collided with some object at a certain position. So we get really detailed feedback that we can then use to adapt either the fabrication system or the fabrication layout in order to get a feasible combination. And one example that we see here on the right hand side, where we have this obviously not very smart setup, where we have this column in between, and one simulation result is, for example, that the simulation environment will detect collisions with the environment here. And yeah, this approach really allows us to iterate really fast over different variants of layouts and tasks, and at the end eliminates the whole human part in the setup of the digital twin, allowing also some closed loop optimization that we could now add in the at the end in the next steps in order to bring this work or advance this work further and really find an optimal solution in between fabrication system and fabrication tasks. Now, so for now, we just using pre-configured fabrication modules, we can automatically set up the simulation environment, the digital twin, carry out the simulation, and then get feedback from it. And in future work, we really want to advance that and generate the whole simulation model at once, where we also just do not use pre-configured modules anymore, but also can generate the whole modules with the whole 3D data, kinematics, and everything in one step. So thank you very much, and now I'm open for your questions.